there. Okay, if I've done everything right, you guys should be able to hear me. At least starting the stream a few minutes early so that way I can see what all we got going on. Okay, everything looks to be fine. We'll just sit here and chill for a little bit. Do that, and I know you guys cannot see my face, but you can hear me. I'll show my face in like 2 minutes. I'm just getting us all links to things. Okay, looks like the OBS integration doesn't quite want to work well for me, but at least for the chat. In the meantime, though, we'll just go ahead and go with chat open over here. There. 59, give a minute, and then we'll just get started. All right, well, it's about 2 o'clock. Not entirely sure if people will truly show up to this or not. And that's okay. I wound up basically making the stream on my phone to start instead of the computer because I was away from my computer whenever I had to make it. And apparently, it wants you to just do it from your phone. You can't just say, like, start from the phone and go to the computer. So that's why this is here. Good news is, though, that's why there's a recording. Otherwise, we'll wait and see if we have some folks drop in. In the meantime, I guess I'll just start talking about what we're up to. So this whole stream is about a framework called PiPPy. And PiPPy basically is all about what's called pipeline parallelism. It's a framework out of PyTorch. They recently started redoing it as sort of a version 0.2.0. And essentially how this works is, say you have a model that can fit on multiple GPUs, rather than sending in one input at a time and having it go through the first GPU, then the second GPU, and then you get the output, and you basically go through this loop. The idea of pipeline parallelism is you say, okay, GPU A over here has a, in this case, quarter of the model. GPU B has another quarter, C and D. And what you can then do is use a scheduler of sorts that says, okay, I'm going to start with the input going to GPU A. After it's done with that, I'll send it off to GPU B, and then GPU A will get another input. And so you're running essentially a bell curve of inputs at a time that can be processed. And so you can get a larger amount of data processed faster using the same compute overhead that you've been using. Right? An easier way of saying that is I can load a model onto two GPUs, send in two inputs, and it will be faster than sending one input in twice through those two GPUs and waiting. Now, where PiPPy comes into play is it used to be rather difficult to get this actually working. Otherwise, you would need to use much heavier abstractions like Megatron or DeepSpeed, where you're kind of using not even a sledgehammer, you're using a bulldozer to put in a nail, right? Because these are APIs that are designed to train models on very big compute, but inference wise, not as much. And on top of that is this whole dependency that's either outside with Microsoft or a variety of other people, where you have to rely on them, whereas everything here is still in-house with PyTorch in a sense. The way it works is you essentially tell PiPPy how you want to split the layers. It traces it based on some example arguments. And this tracing basically helps us keep a graph of how the inputs need to be passed in at certain times and when they need to change devices. And then it works just like calling your model normally. Now, the reason we brought this into Accelerate is, as you're sort of noticing here, there's a lot of code, right? And there's a lot of scary code, especially if you're just a beginner user or you want something similar to what we already have with device map equals auto with big model inference, right? That's how we take, say, Llama 7 billion and load it on, say, two 1060s. Or I guess it'd be two 2080s. So what we've done in Accelerate is essentially wrapped around this with a prepare PiPPy function. It does a chunk of magic behind the hood. Instead of having to explicitly state where your split points are, if you just say split points equals auto, which might change in the future, it'll look at your model and figure out exactly how it needs to split the weights up onto each GPU. So in the cases that we're looking at here, right, you can see we have BERT, GPT-2, and T5. Well, I'm running this on two 4090s. 4090s can run like 10 of these at a time. But the point here is just an example of showing how the split methodology works. And on top of that, showing that no matter what size your model is or what you're doing with it, it will just always work. It doesn't necessarily have to fit on multiple devices. We can just make it split. So what you need is, of course, a model, your split points, and then as I mentioned earlier, some arguments. In this case, it's just an example argument, and also this whole tracing thing that I mentioned is done on the CPU. It's not done on the GPU. That's how we can avoid running out of memory. PiPPy is very nice in the sense that we can do this tracing on the CPU and then transfer it to the GPU when we're ready. But first, we need an example input to trace with. For BERT, we can just do a 2 by 512 tensor that has a maximum value of the vocab size. Now, one very key important part with PiPPy is when you pass in the example arguments, essentially you have to you have to always use this argument setup when you're deploying your model. Um, in other words, arguments that were there during prepare PiPPy must be there when you're doing your actual inference. So here with the BERT baseline case model that we have here, I'm always expected to just pass in some input IDs. And so this will work in deployment in that sense. Now, if we remember how that chart looked, we start on the first GPU and then go to the second, third, and fourth. So all of the inputs has to be available on the first GPU to be transferred, which also means that they're all made on the same GPU at the same time. They're not made on different GPUs and divvied up after. So it works a little bit different than the like split between processes API that Accelerate has. That's one to look at. But after you've done prepare PiPPy, you can just call model input. And I guess I can zoom in a little bit. You can just call model input like you would normally. Now, as mentioned earlier, don't really use keyword arguments for this. Their support for that is still up and coming. And so it's a bit rigid right now. So, but if your model can accept tuples and just general non-keyword argument inputs, then this will wind up working. So here I just have a very basic script that will just measure the time it takes per iteration. And what I generally found is running on my system. So if we take what is called accelerate or sequential, that's saying that I'm taking the model and loading it with the equivalent device map equals auto and sending in one input at a time to replicate each input going in at one time on each GPU. The inference time after the first batch, because the first batch in distributed setups examples needs to initialize DDP. Otherwise, we just need to actually handle the model cache. So after everything's said and done, with BERT, we get roughly 1/10 of a second. And with PiPPy, we get almost half of that, really like 0.6 of it, which makes sense. We would expect it to be near double since we are using both GPUs effectively. Now, a key thing with PiPPy and how this sort of thing works, right? If we go back to that chart, which I don't have up anymore, if we go back to the chart, remember it's a bell curve, right? So at the end, all the outputs in this case, well, the picture's a little bit not too accurate. It gives us a general idea that we can follow. All of the outputs are up here on GPU 4, the last GPU. Is really what we want. We're not doing any of this over here. We're just doing the forward pass because this doesn't support training yet, at least with the accelerated integration. So everything is on the last process. Now, for speed testing, this works, right? Because we're just measuring how long the speedup is between output A and output B. In the real world, you're going to want to use the gather output equals true parameter for prepare PiPPy. And what that will do is, in a fairly efficient manner, take your outputs that are currently on the last GPU and copy them across to all the GPUs. That way, you don't have to remember, oh, my outputs are only on my last GPU. Now, it does come at a speed cost because there's going to be a communication that's happening with the actual gathering itself, and there's a bit of a few hacky things we had to do to actually make gather work because we don't know the actual output size. If you want me to go into that, I can. It was a very neat PyTorch trick. But using this is a very low code method to let you handle big model inference without being restricted by having GPUs that are just sitting there and hanging. Uh, Now, the other side to this, of course, is at least right now, we haven't fully tested the offloading capability yet. But at least for right now, the model has to fit on all your GPUs. There's no CPU offloading yet, at least in our integration. That's one of the areas that we're going to look at next. Another caveat is it currently doesn't support model.generate, mostly due to that weird keyword arguments thing. But that's another thing that we're going to look at very, very soon. But if you go through the examples, you'll find that here we have GPT-2, exact same call with the exact same API, and it'll work the exact same. And same with T5, which the key with T5 is we have input IDs and decoder input IDs. So actually, let's talk about that for a moment. So T5 is an example of where those keyword arguments matter. So what I mean by this is we'll do prepare PiPPy, and here we're going to pass in example keyword arguments because, again, T5 wants decoder and encoder input IDs. And then we'll pass in similar to the big model inference API, no split module classes as the T5 block. We don't do this automatically because we're going to leave that to transformers to do, as accelerate pretty much gives you everything bare bones. Now, yes, on one hand, right, we passed in the example keyword arguments here. This is fine to do so during tracing, because tracing, you're essentially telling PiPPy, this is how I expect the arguments to be and how they're going to come in. During inference, that does not mean we also then pass them in as keyword arguments. If you look here, we are going back to a tuple. And then we're just passing that tuple in to the model. So it's a very weird API there in terms of certain things have to be different. Well aware of that. Not much we can do on the accelerate side for right now, but at least it doesn't hold you back from using models that can require it, such as T5. But that's essentially all there is to it. There's another example here, which also I've linked links to this example section of the accelerate repo in the chat. Mark, my coworker, got an example going that lets you do llama. So here you can see that we have actual text prompts that he goes through and tokenizes, does prepare PiPPy, and then goes through and does the inference yet again. So we kind of chose to use PiPPy because it was the first real lightweight and straightforward way of doing pipeline parallelism without needing the extra bloat that other libraries tend to have, or at least make it rather difficult to use. So here, there was a question in chat of, are you parallelizing the decoder inference? So essentially what winds up happening, we can take a look at that actually. Let's take a look at what we have going on here. So when you call prepare PiPPy, right, prepare PiPPy is doing this magical split thing where essentially what we look at is it's a very naive approach to generate the device map where we calculate the maximum model size in bytes. And then we look at how many GPUs we want to use. And we take the model size and the shared model size. This is coming from a util and accelerate. Take the sum of this and divide it by the number of processes we have. And hypothetically, that would split our model exactly evenly between each GPU. We don't optimize for having the decoder be on one GPU and the encoder be on another GPU. It's however the split happens, right? Because if you have four, will be like if you have four GPUs, then you'll want to split the encoder possibly onto two GPUs, and same with the other. By handling this sort of auto split method, it should get you roughly there. I know the examples in the PiPPy repo showed this being done quite a lot. Now, on our end, we also found that like in order to get these params quite how they should be, we had to add a buffer. That's just how it wound up going. And so generally what you can then find is we store the device map in model dot how did we say it? It was Hugging Face split points. Let me go through and do accelerate, launch, examples, inference, T5. So you can see here that we are indeed splitting on the first decoder. So it did automatically pick up encoder decoder there. But it just depends on what the model winds up doing, essentially. Very good question there. Let's see. So we have another question. Zach, about the gather thing, because the results of the last GPU, I imagine that is inference oriented. The result will be output from the last GPU, but the CPU will handle the result. So it would be more useful to use the last GPU conditional to handle the results rather than gather in all processes. Hypothetically, yes, that's why we don't do it as a default, right? That's why default is false. But because this is being ran with accelerate launch, like right, this isn't being ran with Python. You can't do that. It has to be using a distributed launcher. You need to know that you're working still on the final node, which accelerate is designed to be a minimal to no thinking library when it comes to what is on what process, right? That's why we generally don't have any code until you start getting the nitty gritty of checking, oh, are we on this process? Oh, are we on this process? Let's do this particular thing. So for users that want to keep that, they can gather the output. It might, again, as you state, not be the most efficient thing in the world, nor necessarily the most quote unquote realistic thing in the world in development standpoint. But I at least believe that having it as an ability in Accelerate is still important because I can fully very easily see people taking that off of the CPU and sitting there wondering why some are none and why some actually have values depending on which spawned process you're on, right? Which GPU process. They could always use a conditional, and that's totally fine. That's why we advertise using it. But for users that aren't, and when they want to, and we want to lower the barrier of entry a little bit, that is why you can still do this gather outputs. That's a very, very good question. And I do appreciate that feedback. That's sort of why we wound up going that way. Does it logically make the most sense in the real deployment world? Not necessarily, but didn't want to just ignore it in case it's something that a user might need. Because I am definitely one of those users that I will try and find a million different ways to break things and come up with a weird way of doing that no one prepares for. That was one such case. So if it's useful to other people, great. If not, it's set up in a way where we can either A, change that default value later on, or maybe just get rid of it. But very, very good question, TJ. Let's see. So some other things to note about it. Yes, so as I mentioned, it requires sort of a DDP setup. So you can either run with torch run or with accelerate launch. Generally, torch run is easier because there's nothing really to do in accelerate config for that. But I do know that some people just like running accelerate config without even running the configuration because it handles a lot of things for you. So that's why at least I tend to use it. I don't particularly think there's too much else outside of that with PiPPy. Again, we're still working heavily with this. This has sort of been the results of the last, I think, month and a half between us and the PyTorch team, and sort of figuring out the best way for users to do this while also still leveraging the freedom. Obviously, in the future, we want to fully support pipeline parallel training as well. With Accelerate, ideally, it's the same as accelerator.prepare. How that'll end up looking at the end of the day should hopefully be the same without too much complication. We'll kind of see. But that is all that I roughly have for this. So there's a few example scripts that you can try in the repo. Directions to do so. Links are in the chat. And I guess I can just sit here and answer any questions for a few minutes that folks might have. In the meantime, if there's other folks besides TJ here, looks like TJ might be my only friend. So that's quite all right, though. If there's not any more questions, then I'll go ahead and end the stream there. Again, that's kind of was an idea of when we come out with new Accelerate features, I like to at least do a video version as a light walkthrough of what we have going on, along with a tweet. And you have the docs and you have the examples, but some people do like to learn just by videos, and so at least having a stream somewhere can help out with it. So, thanks, LZ. Yeah, that's more or less all I got. If you wind up having any issues with this, or you're trying different methods and things aren't quite acting as you think they should, go ahead and open an issue in Accelerate and ping me on it. We're actively keeping an eye on sort of the response to this PiPPy integration, and so we'll definitely get back ASAP on that. And if you find something that breaks, that's even better, because it is a bit rigid in some ways as we were learning it. So finding more edge cases where things aren't quite working good is always beneficial. Yeah, TJ, we've had plenty of people that have asked already about, like, does it support training? And most importantly, does it support generate? Which, like, we're working on it. We're getting there. Lots of things that we're trying to put in place right now. But hopefully that should come within the next few months, ideally. So, yeah. All right. Well, thanks for joining, everyone. I'll go ahead and end the stream there at about 30 minutes. Rohan, you're joining right at the end. I'm sorry. But yeah, thanks for joining. As always, it'll be linked on the channel for you to go view at any time. And I'll be sure to include links to all of the GitHub repos and probably my tweet explaining everything in the